challenging to get here, especially if you don't have an umbrella. And Gabe, do you have a raincoat later?
I'm willing to get wet on my way home.
So yeah, really great. Appreciate your guys' support, and I think you will get something back, and at least God will bless you. Will do good in next week at least.
Thank you.
Okay, so let's get started. So this week we'll cover chapter 7. But since chapter 7 is a really huge chapter, it talks about a lot of stuff in this chapter, and will be a really good sources for making questions, okay, for the final exams. So we'll kind of split into at least 2 parts, the whole with 3 parts to talk in sections. So the first part will deal with mainly about the wave functions. Okay, so next one would be energy, and for any given microscopic system, once we understand the wave functions, once we understand the energy, that'll be enough. Okay, so this is the first part. First one, as you will see, as we saw in previous chapters, we know all those things we'll talk about are all derived from Schrodinger equation. Okay, and for this specific hydrogen atom is another microscopic system, so still we need to know for this chapter, for previous chapters it's okay. You don't understand how we write the Schrodinger equation. But for this chapter, I want you guys to be clear about how we set up the Schrodinger equation. Okay, so this is the question. How can we set up the Schrodinger equation to describe the hydrogen atom? To answer that question, we need to understand the structure of the atom. We know this is the hydrogen atom, so it contains 1 nucleus and 1 electron. So based on this picture, actually, we can write down the Schrodinger equation. So the way to do it is to analyze what kind of energies are in this system and how can we express them. Okay, for example, first of all, for the electron. So just for the electron itself, what kind of energy does this electron have? Think about it. The electron is moving. Kinetic energy, exactly. So the kinetic energy of the electron, right? Only single electron. And it corresponds to, so this energy corresponds to an operator. Do you know what kind of operator? It's called what operator? Corresponds to the classical observables, which is kinetic energy. So that operator is called, well, if we talk about Hamiltonian, it's called total energy. For kinetic energy, it's just kinetic energy operator. Do you remember that? Kinetic energy operator. Okay. One more. How about the nucleus? What kind of energy does the nucleus have? If just talking about the nucleus itself, well, actually, it's still a little bit like vibrating. Okay, it's not, perfectly stationary. But for this case, when we talk about the kinetic energy of the nucleus, we assume it's 0 by assuming that the nucleus is stationary. So that will simplify the situation. Okay, simplify our calculation, evaluation in the future. But I just want you to be clear, there's still a term called kinetic energy of the nucleus. The nucleus is still slightly vibrating there. But compared to the kinetic energy of the electron, this is so tiny, 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 so we can just ignore it. Okay, so assume that's 0. Okay, do we have any other kind of forms of energies in this system? Potential energy. That talks about the interaction between the two. Okay, so potential energy, the corresponding operator is called, which one is correspond to the potential energy observable? But it's not a spatial name, it's just called potential energy operator. Right? And we know potential energy operator is potential energy itself. And this values depends on your specific microscopic system. And for a hydrogen atom, is actually derived from Coulombic attraction. So which is negative E squared over 4 pi epsilon 0 R. Okay, that's exactly the Coulombic force, the equation here. Okay, we have 2 kinetic energies one of them is 0, and we have one potential energy. Do we have any other kind of energies in this system? Do we have others? More than the 3? Do we? That would be great. Express your idea.
Well, doesn't kinetic energy cover both the vibrational
Cover both.
and the rotation?
Cover both. So that complete, right? So then we have actually 3 energy terms, but since one of them is 0, so we only need to care about 2 energy terms. So when we set up the Schrodinger equation, we know we only need to care about the Hamiltonian operator. My other part is just operate on wave function equals total energy times wave function. That's nothing new. So the only tricky thing is the Hamiltonian operator. We know Hamiltonian operator consists of kinetic energy operator plus potential energy operator. And this blue one is kinetic energy operator. And the pink one is potential energy operator. And pay attention, they all have one negative side, so don't forget about the sign here. Right? And then you use the whole thing to operate on the wave function. You get the eigenvalue back times the wave function. Okay? Any questions? So in the next chapter, we'll talk about many electron atoms. And we also need to be clear about how to write the Schrodinger equation. And there, we still use the same trick here. Analyze what kind of forms of energy are in this system and use the corresponding operator and combine them together and form the Schrodinger equation. And we will see. Okay, so this is a really simple system actually because it only contains 2 terms. So the situation is somewhat simple. So now we have this equation, and we know in order to get the energies and wave functions out from this equation, we need to solve it. Right? But unfortunately, if you want to solve this equation in Cartesian coordinates, which means x, y, z coordinates, it does not work. You cannot do it. So we need to introduce this system to another coordinates, which we learned in previous chapter. Is called what coordinates? Spherical. So we transform this to the different coordinates. And you still remember for the Laplacian operator, we have a long expression in spherical coordinates, right? Plug in. And you can get a new Schrodinger equation. And the next step is to separate variables. As you can see, this wave function that later we will talk about is called the complete wave function of hydrogen atom. It involves r, theta, phi, which are the 3 coordinates in spherical coordinates. So it exactly depends on the 3. And we need to use this trick to separate them into 3 parts, or here it shows the 2 parts. So the first part involves just the r, okay, the r part. This one is called the radial wave function, or the radial part of the wave function. And the remaining part here involves theta and phi, is called the angular part, or angular wave function. Okay? Do you still remember the definition of r, theta, and phi in spherical coordinates? Right, first, r is talking about the radial things. It's like the radius of the shell. For theta and phi is talking about the angle. So that's why this is called radial wave function, this is called angular wave function. Okay, any questions?
So the angular wave function, are L and M supposed to be switched, or I always thought that M.
Oh, sorry, it should be switched. So here should be L, here should be ML. Okay, good catch, yes. The next few slides will get correct notation. So here, this is not correct. Actually, if we switch it.
That actually raises the question: what exactly do they signify? Are they just kind of there arbitrarily, or?
It's like the historical reason, or like people get used to expressing that way. If you want to do this way, anyway, it's fine. But you kind of behave differently than others, which is kind of unique, anyway. So by doing so, 2 things. By transforming it to the spherical coordinates, by separating our variables, we can analytically solve the Schrodinger equation. Okay. So analytical also means explicitly. So we can get something. And we can solve it, actually. We can get the real, the root for this equation. We can get energy, we can get a wave function without doing any other approximations, just by doing this. And you will see in the following, in the later chapter, chapter 8, for some of the atoms, not some, for most of atoms with more than 1 electrons, we cannot solve it explicitly. We need to use the approximation method, which is another chapter. Because back here, we don't need to worry about that. Okay, solving Schrodinger equation in this chapter in here for hydrogen atom is not required. Okay, but the thing I want you to be clear, we need to do some special things before we can solve it explicitly. Okay, but the whole process, you don't need to care about that. Okay. So let's say, assuming we successfully and correctly solve the Schrodinger equation, and we'll get wave function and energies. So in this section, we talk about wave function first. And we already know wave function consists of 2 parts, the radial parts and angular parts. So let's take a look at the radial parts first. So the general equation, with the general solution for Schrodinger equation in the radial parts is given in equation 7.14. And this exact expression is not required. You don't need to worry about that. And you don't even need to remember it or just understand what each terms mean. But I want you to be clear about what does this function depend on. Okay, this function depends on n and l. Those are 2 quantum numbers. Okay, and what's the name for n? Well, we'll talk about that. Okay, we'll give you some time to think about it. And what's the name for L?
Rotational quantum?
No.
Angular?
Angular what? Angular momentum quantum number. You got that, but you forget about N. Give you some time to think about it. Okay. So for some radial wave functions, also they are shown in table 7.2 by plugging different N and L values. In plugging N, in plugging L, you can greatly reduce this part, reduce this part, reduce this. This is a polynomial, and this also, you can reduce it to something like that. And also, you don't need to memorize all the things. If we want to give you a question using those equations, we definitely will give you the wave function. So 2 important quantum numbers arise from the equation I showed you before. So to describe a quantum state here, we need actually a set of quantum numbers. And what we used before are just 2 of them. Okay, there are actually 7 quantum numbers. And in this part, we'll only talk about actually these 2, but later we'll talk about ML as well, because it's in the angular part. Okay. So now comes the question again, what's the name for n?
Principal quantum.
Principal quantum number. Got it, okay. We'll talk about in the next section about the significance of all those quantum numbers. Okay, it actually tells you something. How about L? You already said it's the angular momentum quantum number. And sometimes in order to distinguish L and S, we'll put orbital here. So it talks about orbital angular momentum quantum number. Okay, it's a noun name, but if you say just angular momentum quantum number here, it's okay. But after we learn S, we need to put orbital. And what's M and L?
Magnetic?
Magnetic quantum number. Okay, magnetic quantum number. And because this depends on L, okay, this depends on L. So also we need to put orbital angular momentum quantum number. Somehow in order to distinguish MS here. Okay. Those are non-names, but anyway, if you say magnetic quantum number right now, it's okay. All right, and out of 4, let's left to the next section. And we know they have some possible values. They cannot be everything, right? N, L, and L. So what's the requirement for N? The N could be what? Can N be 1.1? 1.2? So they must be integers, right? Integers from
0.
okay. Integers from not from 0, sorry, not from 1. You cannot have 0 as n. Remember? How can you have 0 as orbital? Right. Okay. How about L?
0.
They're all, so first thing, they are all integers. starting from
0.
0 to
N minus 1.
minus 1. Okay, it cannot be larger than n minus 1. Okay, that means if n equals 1, your L can only be 0. Right? So from here we will see n cannot be 0. So if n equals 0, L equals negative 1, that's impossible. Okay, and how about ML? Should ML be also be integers? Yes. And they are from what to what? From 0 to
Plus or minus 1.
minus 1 plus
Plus or minus
something.
2.
So since this is about a symmetry, there's something like symmetry about 0. So you have 1, you have minus 1, right? So something like that. So let's say it's 0 plus minus 1 plus minus 2 to until what? Plus minus L. Right? So if L equals 1, n can be 3 numbers. So 0 plus minus 1, that's 3. And again, in total, they have 2L plus 1 and L values for a given L. Okay? For other 4, let's left to the next section. Okay? And based on the 2 important quantum numbers, n and L, we can actually introduce another thing called the orbital notation, which is just NL. Okay, something like here. 1s orbital, 3s orbital, 2p orbital you use in your dream tab. Those are called the orbital notation. It's just NL. So as you can see, the first one, the number is n. Okay, from this one, 1s means n equals 1. 3s means n equals 3. 2p means n equals 2. But the weird thing is s and p, what does that mean? If they would have a list for each L value. If L equals 0, the symbol is s. If L equals 1, the symbol is p. And 2 for d, 3 for f, and more. Okay. And the common mistake student will make is forget about L can be 0. So once someone say, oh, L equals 1, oh, that's s orbital. So pay attention here. So we have L can be 0, and 0 is actually s, 1 is for p. Okay, we'll see that here. You probably will make this mistake as well. But just remind yourself, smallest L value can be 0, and 0 is s. Okay. So let's do one exercise for 3D orbitals. Can you tell me what's n and what's L? Straightforward. N equals 3 and L equals. Don't look at 2. Okay. So someone would say after several days, so if I ask this again, someone say L equals 3 because SPD 1, 2, 3. Well, from 0. Okay. So let's take a look. 1s orbital. Okay, 1s orbital is kind of simple. Okay, we talk something about that, and also we talk about the same orbital in the textbook. So let's spend some time here. So the wave function for 1s orbital, I mean the radial parts. Okay, the radial parts is R1, 0, R. So here it's just NL. So for 1s orbital again, n equals 1, L equals 0. So that's why R1, 0. Okay. The general expression is like this, and also normalized. So this is normalization constant. And we know this is the exponential decay function, right? E to the negative R over A0, or A norm anyway. If you plot the R function versus R, you get exponential decay function. So when you go to the infinity, so I have to ask something. So this figure is actually constructed from the picture or the plot of the wave function. So we know 1s orbital is as a vertical. It's just a sphere like that. And we started so here's 0 means 0 here. The physical meaning is we set the 0 to be the position of the nucleus. Okay, this is the hydrogen atom. So we set the position of the nucleus to be 0. So that just means the center of this wave function. And we plot the R direction is we go to the infinity. So whatever arbitrary direction you want to go, they are symmetrical around the all angles. So you can go one direction to infinity, and that's the positive direction for R. And along the way, we can measure the different probabilities, by using this wave function, and we can plot this one. And that's exactly shows you the picture. Okay, so there are several things I want to mention. So the first thing is the maximum point for sure is at r equals 0. Okay, this will give you the maximum point of this. And we know if the wave function r goes to infinity, I mean positive infinity, what should r want 0 to approach? If r approaches infinity, what does r want 0 approach? 0 as well. It's go to 0. The decay to 0, but to the infinity far away place. So that simply means for one electron, not for 100 atoms, the probability for finding that electron in the atom infinity far away place is 0. You cannot find the electron there. And in other places along the way, you have some probabilities. But the probability you can see after decay for some locations here will be quite small. Okay. And this one, the turn for somehow this one is not quite far. It's probably like nanometers. I don't know the exact value, but probably within nanometers. So simply means you grab that height of the atom here, and I just step about like 1 centimeter away. It's quite far away for the height of the atom, and can be treated as infinity, not far away place. Okay. But just give you this idea. The infinity here is not that real infinity. Well, it's still the real infinity, but it's not like quite that long. You don't need to be that long. Just be like 1 centimeter or 5 enough. Okay. So I want to ask a question regarding this equation. Okay, this wave function. What is the maximum probability to find the electron in 1s orbital? R equals 0. How can you tell that? Well, first you do, I know, first you want to square it, right? Let's talk about probability. You know, for just a given wave function, it's not a probability. Based on the quantum mechanics postulate number 1, right? The Bohr's interpretation wave number. This is a probability. So we talk about the maximum probability. Of course, we need to evaluate the product first. And since this is the real function, just square it, you get this wave function. And you can again plot the wave function as this, it's still an exponentially decay function. And of course, this question says r equals 0 will be the maximum probability, right? Right? Think about this picture. Or let's go back a little bit. Anyway, let's go. I don't need to go back. So the maximum probability we talked before is r equals 0. Tell me what's the physical meaning of r equals 0.
Well, like there's no distance between the proton and the electron.
So that simply means the electron hits on the nucleus, right? R equals 0 means just the location of the nucleus, what I defined before. So here you tell me the maximum probability of finding that electron is r equals 0. So that means it's on the surface or it's just inside of the nucleus, right? So this will happen, right? So that the electron heat on the nucleus. You bring the negative charged species to the positive charged species together, and that will create something I cannot imagine. I will release a lot of energy. Does this make sense to you then? Why we can see stable hydrogen atoms there? Why they do not explode? Why they do not decay? Why they do not collapse due to the attraction? Right? Why they can stable there? What happened? What's wrong with our quantum mechanics? We use a probability density evaluation. It clearly tells us the maximum probability to find the electron is inside of the nucleus, which actually is not true. If you learn from Chem 1B, you know this is not a correct picture. So what's wrong here? Well, the problem is, maybe ask you, how can we normalize the radio wave function in spherical coordinates? In spherical coordinates, how can we normalize it? If I give you a radio wave function, I ask you to, since we use R, so you know it's used in the spherical coordinates. So how can we normalize it? I get years. First, it should be an integral, right? From where to where? the bounds. What's the possible value for r? 0 to what? All the way to infinity. And what? Go on.
R squared?
Square, or let's use this square. Okay, to be safe. And what? dr? dr? That's all? Constant, okay. That's all? That will give you 1? That'll give you 1?
So we need to convert from Cartesian to sphere.
It's already in separate coordinates. To give you 1? Remember? The detail in separate coordinates is 1. What I emphasized last section, okay? You sometimes we do it. We have additional terms coming up. Remember that? That's how we do the normalization. We have r squared here. So it's no longer what we learned in chapter 4. In chapter 4, we use Cartesian coordinates. We don't need to care about any additional terms. As I mentioned in last section, when we're doing some normalization or whatever, we use the volumetric unit here in separate coordinates. We need to think about r squared and sine theta for theta phi. If you ever talk about r, we only care about r. So we have r squared actually. So which means when you do the integral, you do this one. The 3 product here, not just for the 2. So the probability in radial direction is, in spherical coordinates, is r star times r squared. Okay? And based on this equation again, let's rethink the previous question. The maximum probability for finding the electron now is not r equals 0, because if you plug in r equals 0 here, what will happen? There's r squared here. That will reduce to 0. So it's actually 0 probability for you to find the electron there, which makes sense, right? How can you find the electron inside of the nucleus without destroying the atom? Well, that makes sense now. And also based on this figure, you can actually predict what does this probability look like. So we know r squared, this magnitude square, it exponentially decay, right? And times r squared is a parabola. That's r squared. So if you combine these two, in math it will tell you if one thing goes down, one thing goes up, you times the 2 functions together, you will have a maximum point somewhere. And that is r squared times or later r squared. So we can predict actually for one s orbital, the probability density distribution looks like this. Okay. So my drawing is not quite fancy, so we have a fancy picture in your textbook. So this is actually the 1s orbital. So it looks like that distribution. Okay, that's a more fancy one. So again, 1s probability density distribution is at r equals 0 is 0. At a certain point, we reach the maximum point. That's what I showed here. And then exponentially decay to 0. Okay. And the maximum point here corresponds to a certain r value. And the r value, when talk about in separate coordinates, is the distance between that electron with the nucleus. Okay. And similarly, at this radius, we have the maximum probability to find the electrons. And this radius is called the Bohr radius, denoted as A0 or A norm. And A norm here is actually the one in the R function here, this one, and this one. Okay? So any questions about this? Any questions? Good. Okay, I hope you understand this. It's a little bit abstract, but once you understand, once you pay attention to the R squared there, it actually makes sense here. Okay? Besides 1s, we also can draw use different wave functions for 2s, 2p, 3f, 3p, 3d, and we get those distribution curves. Again, use the same thing. Use r squared times r squared. Okay. And if, last year when I taught this class, I did the section, students asked me, for hydrogen atom, we only have one electron, and that electron is in 1s orbital. How can we have 2s, 2p, 3s, 3p, 3d, even 4? Those orbitals here. Why not just 1s orbital? Right? You have the same question. Do this pictures look weird to you? But we only have one electron, and that electron must be filled in 1s orbital, right? How can we have those orbitals here? And they actually can show you probability density, what happens. Maybe anyone can answer my question? Have you thought about this before? I believe some of you will try to believe that the hydrogen only has 1s orbital, right? It only has one electron there.
Can't that one electron get excited to the other?
That's right, that's what I want to hear. So it can be promoted to the electron. What you thought before is just for ground state. For unexcited state, you only have one s orbital. You only have one electron in one s orbital. But don't forget, we can excite the electrons to higher orbitals. So that means the orbitals, they are all there, but they're just empty. Okay, one s orbital is still there, but they just filled with one electron in ground state. But there's still rooms there, and the electron can have to be promoted to those rooms. Okay, although they are empty, you cannot say they are not there. Right? It still exists, but just empty. So no electrons in ground state. Okay, so the first thing I want you to be clear. And then I want you to count something. Like while we practice in modeling the box again. So the first thing I want you to count the maxima value. Okay, here I mean maxima value, not just for one maxima, but for all those peaks. For the top one, the summits, for all those peaks. We all count as maximum. Okay, I know the name is not quite accurate, but anyway, we just counted the peak. The peak number, let's say the peak number. Okay. So for 1s, how many peaks we have?
1.
And for 2s, 2. 2p, 1. 3f, 3. 3p, 2. 3d, 1. Can you give me a relationship between number of peaks with those quantum number n and l? Okay, let's do it together. For 1s, what's n?
1.
N equals 1, what's L?
0.
L equals 0. So we have 1, right? Can you imagine? N equals 1, L equals 0, we get 1. For 2s, we have 2. N equals 2. L equals
0.
0. So we have 2. For 2p, we have 1. N equals
1.
2p.
I thought you said L.
N equals 2. L equals 1.
1.
And we only have 1. Somewhat like n minus L, right? Okay, let's check again. For 3s, n equals 3. L equals 0. So 3 minus 0, 3. That works. 3p, n equals 3. L equals 1. So we have 2. So n minus L. For sure. Okay, the first thing. The number of peaks equals n minus L. Okay, the second thing I want you to count is how many nodes we have for each figure. Okay, how many nodes? So for the first one, how many nodes?
0.
Well, someone will ask me or ask you, so hopefully all of you can answer the question. Why not count 0 here? I mean add 0, and why not count 0 at infinity? That's still 0. Why not? Right? And you say, expand that, you say 0. But actually, someone will say we have 2. 1 here and 1 to the infinity. Can you answer that? Think about parting in a box. Parting in a box. We have 2 boundaries there, right? At boundaries, the wave function is still 0. But did we count that as a node? Same thing here. The boundaries for hydrogen atom also 2. One is the center of the nucleus. Another one is infinity. So although wave function at these 2 positions are 0, but they are boundaries, so we don't even count them as a node. Okay? When you understand that, can you tell me how many nodes here?
1.
Where is it?
Between the two.
Okay, not this, okay, just this. How many nodes here? 0. How many nodes here? 1, 0. Can you give me a relationship between the number of nodes with quantum numbers here? N minus L minus 1. So for each figure, the node number is peak number minus 1. So the number of nodes is N minus L minus 1. And those are very, very important. So I want to frame it with golden color. And I guarantee, okay, in money back guarantee, you will have some questions. If not in the final, but also in the quiz. Okay, for this thing. But we will not kind of test you in this way. This is so straightforward. It's like parking the box. We really practiced it before, right? Remember the second question in the midterm shows you a wave function and you just need to count the node. Well, for chapter 7, we upgraded. Okay. We do something. We extend this figure into a two-dimensional picture. So we extend to two-dimensional picture. So think about it. So this is actually just a cross-section. And for a hydrogen atom, it's spherically symmetric. And remember when we construct those figures here, is actually I define this as an origin point and go whatever direction I have, right? But actually I should rotate it to 2 pi degrees. It actually forms a circle. So something like that, for example here, this figure, I should rotate it for 360 degrees, and when I look, observe from the top, I will get a picture like that. You understand this one? Can you understand the transition here? So this figure only tells you the cross section. So it's like a pie. Okay, like a pie. I cut it, and I observe from the side exactly gives you this one. But now I want to recover the pie. Okay, I take the pie and rotate 360 degrees and observe from the top exactly give you this picture. And there's a peak actually. There's a peak in this figure, so there's actually like a peak ring in this picture. And the different darkness for the color is representing the probability. So if it's darker, the higher probability. So we will see actually there's a blurred kind of peaks or a ring in this figure. And if you measure the distance, it actually gives you A0, exactly Bohr radius. Right? Understand the picture? So that's actually the real quantum picture of a hydrogen atom 1s orbital. It's everywhere still have probability, but there's some denser or the higher probability to find the electron at r equals A0. Okay? So this is a real quantum picture. Understand this one? A little bit abstract, okay? You still remember the Bohr's model when we talk about hydrogen atom? So he believed that we have one s orbital. And the orbital without thickness is just a solid line there. Like this one, a pretty clear orbital here. And the electron will kind of rotate around the nucleus. Is this true? Make sense there? Compared to this one, make sense? Huh? Kind of, but not accurate, right? Not quite. So Bohr actually messed up with the probability. So from his picture, the early picture, he did not consider about probability distribution. And in reality, we have probability distribution here. So it's not a solid orbital, it's just a kind of blurred picture of that. And all of those are probability, not about an orbital for the electron to kind of move within the orbital. Okay? But because this model is so famous in the early times of quantum mechanics, so people kind of use the word orbital to describe here. Like here, I want you to be clear, this is not the so-called orbital. It's just actually it's like higher or larger probability region for the electrons. Okay? So that's also is a classic quantum picture. It's a real quantum picture. Okay. Same thing for 2s. I can also use the same trick and I will recover the real picture like that. And from here you will see we have a dark region. That dark region is actually this one here. And this is called what? This point is called what?
No.
The node. So the node in this cross-section picture, when you rotate 360 degrees and you observe from the top, you actually see a wing. That's also a node. Okay, you have to see the node. So there have a higher or like a, like some different colors represent different probabilities. Okay. So this is actually the pure quantum picture for 2s orbital. And you remember for Bohr's model? There's still one orbital there, right? 2s. The only different thing is if actually the radius increases. Does this make sense then? Well, it's getting worse because it only talks about one ring. But actually we have two regions. Okay? We have two peaks here, two peaks. Alright? So that's why when we talk about the Bohr's model, I mentioned to them, this is not a perfect model. It actually does not apply to non-hydrogen-like atoms. So even though for helium atoms, it does not work simply because it failed to consider a probability. Okay, and we know for quantum mechanics, based on the previous chapters, they are all about probability. So you cannot get a correct picture without considering it. Okay, so any questions? Okay, if not, let's go to the angular part. So all the things I told you about radial parts. Okay, so angular parts here, for the wave function denoted as y, we already used it in chapter 6. It's called the spherical harmonics. Same thing here. But the only different thing is we changed the notation. So I think that's going to be a mistake here. So before we used J, right? And now we cover J to L. They have the same physical meaning, but just with different notation and different names. So here L is the orbital angular momentum quantum number. And before we use M here, right? There we say it's magnetic quantum numbers. So here is still, again, magnetic quantum number. But to be more accurate, it should be the magnetic orbital angular momentum quantum number. Okay. But anyway, those are some notation. And so they depend on L and ML. So the previous one, the radial parts depends on N and L. Here the angular part depends on L and NL, still 200 numbers. So how could this wave function be derived in angular momentum? Then you need to use separate coordinates based on this definition. So let's just take a look at y and x, y is a panel. So over you will see. So z y tan here. So the angle of theta is actually defined as this one, right? In separate coordinates. Okay. And we have a line here. For each theta value, I can plug in here. And let's assume phi is a constant or somehow we need to consider that. We can plug in theta in, and we can get a value out, right? So for each given specific theta, we set the length of this line is actually the y. Okay, it's actually the function, the value of the function. So for each one, we can get one dot, right? For each angle. Let's say for this angle, okay, this one, or this one, this one. So maybe you can actually practice. And then we can connect all the dots together. That will give us something like that. A dumbbell, or just a sphere, or just something weird. Okay. For example, for d orbitals, you do the same trick here. So by changing the theta here, you get like 4 leaves like this. Okay. And the z-axis with the y-axis here is the theta. So simply for this picture, how can we draw it? Easy. So we just choose one theta value, and we plug in to the wave function of the d orbital here. We have the angular form of the spherical harmonics for d, this orbital. We plug in and we'll get a value, and we set the length of this line is the value of the y for each theta. So for each one, we can do it. And it'll give us this picture. Okay. There's something on YouTube. There's a video to show you how you draw the harmonic spherical harmonics here. So that's the thing we didn't show you in chapter 6. Remember, I said in chapter 6, we only talk about the expression. We did not show you the figure. So here is the plot. Okay. And based on this, I want you to tell me how many nodes. So there are still some nodes there. How many nodes in this figure?
2.
Where are the 2?
The one that.
Can you describe them using theta value?
Theta equals 0.
Theta equals 0.
Phi equals 0.
No, we don't need to talk about phi. We have fixed
Phi
phi.
equals
Theta equals 0. Theta equals 0 is where?
theta.
In this one, right?
Yeah.
Theta equals 0. And another one,
Or 2.
pi over 2. Okay, those are the 2 ones. So this one corresponds to theta equals 0. This one means theta equals 2, pi over 2. Okay? And the number of nodes is 2. How about the L value for this orbital? SPD
2.
0, 1, 2. Okay. So simply means the number of nodes in angular direction is L. Okay, angular nodes, the number of angular nodes is L. Okay. Trust me, it works for other d orbitals and it works for other p and s as well. Okay. So without looking at the figure, can you tell me how many angular nodes should this orbital have? How many angular nodes?
4.
4?
3.
L equals what? SPDF. 0, 1, 2, 3. So that's the angular node. Should have 3. Okay. Without looking at the harmonic suffix. No, sorry. Without looking at the spherical harmonics, you just knew. You can guess there are 3. Actually, there are 3. If you go online, you search 4S, 4F orbitals. I don't know. There are 5 orbitals here. I don't know. One of them is just 3. I don't know. Okay. The nerve. Okay. So the 5D orbitals. Well, actually, I asked you the question. 5D orbitals should have how many angular nodes here?
2.
Huh? D orbital? L equals what?
2.
2. So you have 2 angular nodes, right? Really? Everybody agree? Those are the 2. We have 5. So sorry, there are 7. So here are 5. There are 5 D orbitals. Either of them has 2. For example, this one, 2. And this one, 2. So this shows in the 3-dimensional picture. What I showed you in the previous slide, we have 2 lines there, right? They're just in 2-dimensional picture. So if we extend to 3D, the line will be extended to a plane. Same thing here. We have 2 lines in 3D. So you can imagine you have cross section. This 2 line will be 2 lines. But here, if you extend to 3D, like that. 2, 2, 2, 2. How about this? It looks weird. It's still 2. The 2 nodes are actually 2 cones. Okay, there's cone. One cone here, one cone here. Also 2 nodes. So this picture I want to tell you. So don't imagine the angular node, the pan, would just be a flat pan. Some of the nodes can be a cone. Okay, can be a cone. Okay. So since we talk about angular part and also radial parts, once we combine them together, we will form the completed part. I mean combining not by just adding them together, but by multiplying them together. So we'll get this one. So the common notation is NL and ML for the 3 quantum numbers. Depends on our theory and phi. And some textbooks, also our textbook, and also the lecture notes, we use Dirac notation and just use these 3 quantum numbers to represent one wave function. And all those wave functions are shown in your table 7.3. And here I just show you first 4 of them. Okay. And also again, you don't need to worry about memorizing all those things. Once we ask a question, it gives you the wave function for you to use. Okay. So here I want to talk about this one. The very famous questions in this chapter. And I guarantee, again, money back guarantee, we'll have at least 1 question. If not in the final, well in the quiz. Okay. And you will see actually in their homework, problem set number 5, I think. The first question is like this. Okay, is what? To determine the hunting orbitals by looking at wave functions. Okay, by looking at the complete wave functions. What we need to do here is, well, before practicing, I want to tell you the general guide, guideline for doing such problems here. First thing is when you count the number of all nodes. Here I use the word nodes. Simply means there are two things. The radial nodes, well, they are circles. Usually the wave function will be shown to you in a two-dimensional picture. So then, if once you show in a two-dimensional picture, we know radial nodes, I told you before, right? You rotate 360 degrees will form a circle. Okay, those are civil circles, and we know the number of the radial nodes is n minus L minus 1. You already told me before. And there's the angular nodes. In a two-dimensional picture, it's just straight lines. And what I showed you before, the d orbitals, they are crossing here. Okay? And you already told me the number of angular nodes is L. And actually, by counting the number of different nodes here, we will be able to evaluate n and L. Right? Think about that. If n minus L minus 1 equals some number, this one equals some number, we can get n and L. Once we get n and L, we know the orbital notation. It's just n, L. Okay, so the first thing is, if the wave function is spherically symmetric, or is just a sphere, it must be s orbitals, because s orbital is independent of angular part. So angular part is uniform everywhere, so it will form a sphere. So those are something like that. Okay, one s orbital, a sphere. Two s orbital, a sphere. Three s orbital, spheres. And this is showing you a three-dimensional picture, but if you just look at the cross-section, you'll get a circle, right? But the only difference is they have different number of nodes. For 2s orbital, can you tell me how many radial nodes we should have? 1. We have 1. So n minus L minus 1, n equals 2, L equals 0. 2 minus 1 equals 1. Well, that's why we have 1 node here. For 3s, we have 2. So 1 here, 1 here. And for the angular nodes, we should have how many? 0. So can we find a straight line which is a node? Can we? No. Okay. So that's why spherically symmetry, then it must be s orbitals. And the only thing you need to consider is the radial nodes. And radial node equals n minus 1 because L equals to 0. Okay. So 0 node, 1 node, 2 nodes. Okay. For example, what's the orbit of this? So the first question is this one is spherical? Is this one spherical? Of course not. So this part is not like this part. Right? They're not spherically symmetric. Okay, so then we need to count. Okay, don't freak out. It's not s orbital for sure, but we can still do it by counting the number of, let's say first, radial nodes. How many radial nodes we have?
2.
How about others? Did you figure out how many radial nodes? Radial nodes should look like what? Circle. Okay. Can you put a circle which represents the node? Well, the first one I think most of you is like this. Okay. First one now. Do you have one more? Over here. The inside. Okay. And you will see there's actually a bright dot here. That's actually the nucleus. And we use to represent the nucleus here. So you don't need to care about the inside one. It seems like there's a circle node. That's not. It's just the nucleus there. So we will have 2. Actually, I showed you the. I already showed you the angular nodes. So we have 2 radial nodes. And we have 1 angular node. That's here. The angular nodes are always straight line, right? So we can put a straight line here, or we cannot put it here, or we cannot put it here. Okay, there must be 1 here. But we know there are 2 radial nodes, but only 1 angular node, right? 2 radial nodes, what can we get? 1 equals 2. What's the number of radial nodes? Cannot remember? Can you
So
check
what's
that?
your question?
So the two radial nodes here, right? So what can we extract from this one? We can get a one expression.
You can get the n.
Yeah, we can, and tell me explicitly y equals 2 then. And minus L. Can something we put an expression here?
And minus L minus
And minus L minus what? Minus L equals 2. And we have one angular nodes, right? And y equals 1.
L.
L.
So then n equals what? N equals what? L equals 1.
L equals 1.
N equals
3.
4. 3.
Four is 3. Oh, you said.
4 minus 1 minus 1 equals 2.
I was trying to make an equation not knowing the L.
Okay, let's two together. Well, that's something, usually this question will be express your answer in one sentence or in one, just write down the notation. So you already know this, but your final evaluation n equals 3, then you lose the whole point. It's not worth the time, right? So then can you tell me what's the orbital?
4p.
Give me an orbital notation
4p.
For that or for.
for this, for this.
Yeah, 4p.
For n equals 4, so you 4 something. L equals 1 as p. P. Right? This one equals 2, this one equals 1. Therefore, n equals 4 here. Well, we have several exercises to practice in your homework as well. Okay. Any questions? Any questions?
Yeah, for the homework, so if it looks, we don't have to worry about the magnetic quantum number.
No, that's here now.
So, alright.
Here's no. Here we don't talk about magnetic is something else with magnetic field.
Okay.
Here we talk about without magnetic field. You don't need to.
Because in the homework, there's like a bunch with the same orbital notation, but they look very different.
Yeah. Yes. Yes. Okay. Any questions? If not, we have several exercises to practice. Okay. Orbital. Give me some time to think about it. 4.
As long as.
Any ideas?
4s.
They say it's s orbitals. Okay, why? Vertically symmetry. Okay, so must be s orbitals. Good. And how many radial nodes?
3.
How many radial nodes? 3. 1, 2, 3, right? So n minus 1 equals 3. N equals 4. So it should be 4 s orbitals. Okay. And here. But I don't know whether I enabled this one. So somehow this figure is a little bit tricky because you kind of want to highlight the nucleus position. So you want to reduce the color a little bit. Okay. But in the text, we will not give you something like that. So here is a little bit tricky. I don't know. So here I cannot label there. So I don't know whether it's a node or not. It seems like this is, but it's still that quite dark. Okay. But anyway. Could be 4s or could be 3s. This picture quality is not that good. But once you understand the way to do it is okay. All right. You have more to practice in your homework. Okay. Okay. Next question. Given that there are 2 nodes in a hydrogen atomic wave function, one is spherical and another one is the xy plane. Identify the atomic orbital. Okay, so I can do it. Okay. Anyone volunteer? Want to state your opinion?
3p.
Can you tell others how you did this?
So you that you have L equals 1. So
Well, how could you know L equals 1?
because there's
One of the nodes is in the XY plane, and that's not a,
But we still have one which is spherical.
so, and then the other one is associated with,
The radio.
radian. node.
So here, actually, yeah, I think you're on the right track. It's talking about three-dimensional picture here, actually. Right? We're not in 2D dimensionals. The angular nose is actually lines, and the radial nose is actually circles. But for 3D pictures, the radial nose is spheres, while the angular nose are just planes. Okay, so here clearly they use the word plane and spherical something to talk about 3D picture. But anyway, we don't need to really imagine in our mind to kind of construct the picture. We only need to know the number of nodes. And obviously there are two. But we only know there are two nodes. We don't know how many radial nodes and how many angular nodes. Right? So we need this sentence. So if you are calculation, we have one XY plane, one plane, that means the angular node. So the angular node, AN, equals 1. And another one is spherical, that's radial nodes. So Rn equals 1. Okay, and we know angular node equals what?
L.
In general.
Oh, and minus L minus 1.
Radial nodes?
L, or L.
No, you already messed up. Angular node is L. Radial node is.
Minus 1.
So based on that, N equals what? L equals what? L equals 1. N equals
3.
Okay, don't make a mistake again, okay? So that's what orbital. What orbital?
3 plus L.
So we get N equals 3, L equals 1. What orbital? What orbital? Give me a notation.
It would be 3D.
3. Nobody says 3S, huh? Okay, S. Someone say, okay, L equals 1. Okay, S, P, D, L equals 1. Okay, good, S. No, S is for the. Okay. Next one, given that the radial wave function of a hydrogen atomic 1s orbital is, that's what we saw before, determine the R value corresponding to the most probable location of finding an electron there. Okay, we will not have the time to work it out, but can you tell me how you set up the equation? And tell me the track you want to go to solve this problem.
So that those are wave functions.
Can you write on the blackboard? Don't be afraid of making a mistake. We can learn from mistakes. And how can you determine the most probable R value from your expression?
So,
Everybody do right on your own. Right, okay, we go so far. It's so small. This equals what? Equals what? And we're so far. Answer. Can I just make it more obvious? And so R here. That's your answer, huh? Alright, can you give me more time? you agree with that? Agree with that? We're going to look at that. It's not relevant to this question. Okay. Think about it. So anyone has different ideas than the thing we write on the blackboard? Still agree with that? I agree with that? Oh, yeah, okay. Well, you don't need to work it out. You tell me your track. Which track, what direction you want to go in order to solve this question. In a real exam, you won't have a lot of time to work out the math problem. But here, I just want to make sure you conceptually right. Okay, everybody agree with that? Everybody? I don't believe, okay. So can we just do this one first to see what will happen? Can you tell me what does this equals to? Right? Equals what? Do you see what problem happens here? Once you do the integral with a one variable, what you end up with is just one constant. See that? See the concept here? When you do the integral with respect to one variable, you actually eliminate it. But don't look at that, actually. Look at this. A simple equation here, simple example. You integral with respect to r, then you end up with something without r. Something here. You do the integral using r. You will end up with something which is not r, which is 1. What you will get, you want to solve for r here, you will get 1 equals 1 on the last line. And that's true. It's true, but nothing else to solve this question. See the problem here? Definitely this cannot help you to work out this. I also have to do this is a common ways that people want to go. Once they see probability, or they actually want to solve the probability, but they end up with doing normalization. Then how can we modify it a little bit in order to make it work? We will know the first thing is we need to get rid of integral.
D tau instead of dr.
D tau. No, you already get d tau. R squared dr. That's d tau for r part. Well, the first thing we need to get rid of integral, right? We know integral does not work. It will give you something, a constant. And this is what? Probability density, remember? That's actually probability density. It tells you the probability at each given r value.
Does your star mean average for r?
But most probable things does not mean average. Think about a whole bunch of numbers. We have the maximum number. But the average number is not always the maximum number. But here we ask you the maximum probability. Right? So it's not talking about average as well. Instead, so if we plot this figure, what I showed you before, you will get something like that, right? And we are asking you this point. How can we find it? How can we find this r value? This is r squared, r squared. How can I find the maximum point here?
That r equals 0.
So y equals 0? R equals 0, t is 0.
Well, there was an example that we did to find the maximum for, and
That's something without r squared. But here we introduce r squared. We know that one without r squared does not make sense. So we already abandoned that idea. We use this one. And I will give them a make sense picture here. And this picture makes sense. Okay, so how can I get this? What?
Solve for the, get the derivative of that and then solve for zero. Make it equal to
Right? Yeah. You're right. You have a figure in your mass y over x, y versus x. You have some weird shape, right? How can you find the maximum point in math? That's how you tell her. Same thing here. So you simply need to do d of this stuff over r and set this to 1.
0.
And then solve for r from here, as you will get. Without doing the calculation, you actually can tell me if you pay attention previously. R equals what for this one? R max. I mean, maximum probability for y solvable is what? What? So without doing it, based on what I told you before, R equals what? For y solvable. For what? A non, more radius. Okay. Okay. Okay, I think I have a last one, but we don't have time to. We need to do this one first, and then we do the derivative. And set the derivative to 0. Okay. I have the last one, but I don't have time. I just leave it to you to think about it. This one asks you to calculate the cone angle of this 3D square orbital. Okay. So 3D square is square here. 3D square. Okay. Giving you this, but it's not normalized. Okay. It's not normalized, but asking you to calculate the cone angle. So think about that whether you really need to normalize this or not. Okay. And how can you solve the cone angle? Okay. So much for today. And again, we appreciate you guys for support to come here. It's raining outside.